Today on In Your Face Anatomy, we are looking at electrons, specifically electron shells, ions, and some bonds. So let's get into it. All right, electrons and electron shells. Now, last time we talked about our periodic chart, being able to list those in order 1 through 18, and that will tell us the number of protons, neutrons, and electrons. Now, the only exception to that rule is with hydrogen. Hydrogen is atomic number 1, but hydrogen also only weighs 1 Dalton because hydrogen does not have a neutron. And that's super important, and I want to stress that, especially moving forward. So I've got helium here. Helium has 2 protons. It's got 2 neutrons, 2 electrons. Carbon, 6 protons, 6 neutrons, 6 electrons. Oxygen, 8 protons, 8 neutrons, 8 electrons. Hydrogen, 1 proton, 1 electron. That's it. That's the only exception to that rule, and it's right at the very beginning. It's number 1. So let's make note of that because that's important moving on, especially if we're trying to figure out the weight of an atom and hydrogen is in that atom, then that does become an issue later on. So we want to keep up to date on that. All right. So electrons, of course, are the negative particle in our atoms. And we find them circling around the nucleus. So remember, our nucleus is where we find all of our protons and neutrons. And the electrons are kind of orbiting around that in our electron shells. So when we place electrons, what we need to remember is the 288 rule. 288. So the 288 rule tells me that I can put 2 electrons in the first shell, I can put 8 in the second shell, and I can put 8 in the third shell. And that gets us up to 18, and that's as far as we need to go because we're only learning the first 18 elements of the periodic chart. So if I look at lithium, first thing I need to do is come over here and say, okay, lithium is atomic number 3. So it's got 3 protons, so I know it's got 3 electrons. The 288 rule tells me I can put 2 electrons in the first shell, and I tend to pair my electrons up. It just makes it easier for me. Now that first shell is full, so I move to the second shell. So I put 1 electron in the outermost shell. There is lithium and the electron configuration of lithium. Carbon. So carbon, come over here. Carbon is C6. So that tells me it's got 6 protons, 6 neutrons, and 6 electrons. So when I add in my electron shells, boom, I can put 2 in this first shell, and that leaves me 4 more electrons to deal with because there's 6 in total. So 2, 3, 4. So now I've got 6 electrons. Neon. Neon is atomic number 10. 10. So I can put 2 in the first shell. And then I can put 8 in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. And it's that easy. Electron shells are that easy. All we want to do is make sure that we balance out the number of protons and the number of electrons so our atoms are electrically neutral because that's important. Now, any electrons in the outermost shell we call valence electrons. And we call that outermost shell its valence shell. So valence just means how many bonds is it going to form. So with lithium here, I've got 2 electrons in my first shell. I've got 1 electron in the outermost shell. So this outermost shell is my valence shell. It's always the outermost shell, and any electrons in there are my valence electrons. So lithium has 1 valence electron. Carbon has 4 valence electrons because we have 4 electrons in the outermost shell. Neon has 8 electrons in that outermost shell. Now, the thing about our atoms is they really want the outermost shell full. That's when they're stable. That's when they're happy. So atoms are going to do whatever they need to do to fill up that valence shell, except for a certain group of atoms that come naturally, like neon, with their outermost shell already full. Once the outermost shell is already full, that means neon is good, it's happy, it's stable. It doesn't want to form bonds. It doesn't need to form bonds. It won't form bonds. So neon we now refer to as inert. So inert just means it's non-reactive. It's not going to form any bonds with any other atoms because it's already good. It's already happy. Now, we said we can't change the number of protons. If we change the number of neutrons, that's how we make isotopes. If we change the number of electrons, that's how we make ions. So an ion defined is just an atom with a charge. And it doesn't matter if it's a positive charge or a negative charge. If it has a charge, then we call that an ion, an atom with a charge. Now, we have two types of ions here. So if it is a positive charge, we refer to that as a cation. If it's a negative charge, we refer to it as an anion. So I always just remember that like the plus sign for positive is the T in cation, is how I always made that association. I pretend the T is a plus sign when I write out the term cation. So I know automatically that's the positive one, and if that's the positive one, then the other one has to be the negative one. So a cation is an atom with a positive charge, meaning we have lost at least one electron. Now we have more protons than we do electrons in our atom, so we're going to have an overall positive charge. An anion is where we've lost an electron, or we've gained an electron, and when we gain that electron, we also gain the negative charge that comes with it. So now we have more electrons than we do protons, so we're going to have an overall negative charge with an anion. So let's see what that looks like. So first up, I've got sodium. So sodium is atomic number 11. So I know I've got 11 protons, I've got 11 electrons. We have to follow the 288 rule from the previous slide. Let me change colors here real quick. So sodium as my nucleus, instead of writing out all of the protons and neutrons, I just put Na in there. So here's my first shell. I can put 2 electrons in it. I can put up to 8 in my second shell. We just said sodium is atomic number 11, which means I've got one more electron to deal with, and I'm going to stick it way out here on the end. Now, before I move on, let's look at chlorine. Chlorine is atomic number 17. 17 electrons to deal with. So I'm going to put 2 in the first shell, 8 in the second, 2, 4, 5, 6, 7, 8. That gets me up to 10. I've got 7 more to deal with in this third shell. So 1, 2, 3, 4, 5, 6, 7. All right, now the stage is set. I've got my sodium with all of its protons, neutrons, and electrons. I've got my chlorine with all of its protons, neutrons, and electrons surrounding it. Now I know that I want the outermost shell to be full. That's what makes my atom happy, to have the outermost shell full. And if it's the first shell, we just need 2 electrons. If it's the second shell, we need 8. If it's the third shell, we need 8, whatever that outermost shell is. So when we look at sodium here, 2 in the first, 8 in the second, I've got this 1 electron out here all by itself. So sodium has a choice to make. It can either try to add 7 more electrons to fill up this outermost shell, which is a lot of work, or it can just kick out that 1 electron. Boom. So now we've got rid of that 1 electron that's out here all by itself, because that's just going to be the easier thing for it to do. And in doing so, when we get rid of that electron, now we have nothing in that outermost shell, so it goes away. There we go. And now we're left with the second shell being the outermost shell. So now my second shell is my valence shell, and it has 8 electrons in it. Perfect. That's what we want. We want the outermost shell full. But now we look, sodium has 11 protons, and now it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So 11 protons, 10 electrons means I've got an overall positive charge. So this is a sodium cation, because we've got this positive charge, and the cation is the positive charge, a sodium cation, just because we have more protons than we do electrons. Chlorine, we look at it, it's atomic number 17, we said, so I know there's 17 protons, 17 electrons. We've drawn in our 17 electrons. If I look at my valence shell, my outermost shell here, I've got 1, 2, 3, 4, 5, 6, 7. So chlorine needs one more electron to fill up that outermost shell. So it's going to grab this one that sodium just spit out, whoop, and it's going to add it to its outermost shell. I'll just put it up here. So now I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons in my outermost shell. Chlorine's happy. Now we look, we know we've got 17 protons. But now we have 18 electrons because we've added an extra electron. And when we add that extra electron, we add that negative charge. So this is going to give us a chlorine anion. A chlorine anion. That is ions in a nutshell. And it could be that we lose more electrons than just one. It's just easy to show it in one. But if we do, it's still a cation or an anion, depending on where those figures come out with as far as protons and electrons come. So another reason why we need to be able to put these in order. So we need to know how many protons there are. And then with ions, it's just adding or removing electrons. So the sodium is now positively charged. Chlorine is now negatively charged. Opposite charges attract each other. And now we're able to get into bonds. What kind of bonds are we going to form from the protons, neutrons, and electron configuration that we've come up with up until this point? So I know this is positively charged. This is negatively charged, which means we're going to have an attraction between the two. So we're going to form this bond. That is a shitty marker. Let's throw that away. Not much better, but there we go. So there's this attraction between these opposite charges. We've all heard that opposites attract, positive and negative, opposite charges. So sodium and chloride come together now because of their opposite charges and form what we call an ionic bond. An ionic bond is just a bond between ions. We have to have one cation and one anion, and those opposite charges will attract each other, and that forms the bond between them. A bond between ions is an ionic bond. That is our first type of bond that we need to be familiar with, and it's all about these opposite charges and the ions that are formed. Our next type of bond is covalent bonds. Let me pull that. There we go. Covalent bonds. So we said we want those electrons, or atoms want the outermost shell of their valence shell to be full. So they can either gain electrons or lose electrons, and that's how we got our ionic bond, or they can share electrons. So when atoms share electrons, we form covalent bonds. So covalent bonds, we share electrons, and we have two types of covalent bonds to be familiar with. I've got nonpolar and I've got polar. Nonpolar covalent bonds and polar covalent bonds. But with nonpolar covalent bonds, we share electrons equally. So we see the N in nonpolar. I want you to think nice, or nicey nice is how I think it, because we share everything equally. I get half, you get half of these electrons. We're going to put them right down the middle, split them 50-50. We're going to share them equally. That is a nonpolar covalent bond. And we see that with things like hydrogen. So we know hydrogen was atomic number 1. So it's got one proton. It's got one electron. And if we form a hydrogen molecule where we've just bonded two hydrogen atoms together, that is a nonpolar covalent bond because they're each going to put up one electron and share things equally. With my polar covalent bond, we do not share things equally. Polar covalent bonds do not share the electrons equally. And the main culprit behind a polar covalent bond is oxygen. So oxygen is a polar atom, meaning it's greedy. It will share electrons with you, but it's not going to share 50-50. It's going to hog most of the electrons closer to it. So we can see that in like a molecule of water. So if I go H2O, Molecular formula, structural formula. So if I go H2O, what we need to understand is that when we form a bond, what we're really doing is forming, each of these molecules are putting up one electron. So hydrogen has one electron, it put it up. Oxygen has extra electrons, it put one up. Now, boom. So this is the same thing as this. This is just shorthand instead of having to draw out all of the actual individual dots. But we said oxygen is greedy. So what really happens is oxygen takes all those electrons and pulls them just closer to its body. We're not sharing a 50-50. We're leaving hydrogen out there high and dry. And when it does that, it also pulls the negative energy with oxygen closer to it. So we end up with a molecule that has a little bit more of a negative charge because it's got all of the electrons up this way, and a little bit more of a positive charge out here because we just have our protons from hydrogen out there floating by themselves because oxygen is hogging our electrons. So that's what makes it polar. So polar just means with a charge. And so we can see that overall, a water molecule on the oxygen end is slightly negative, and on the positive end, it is slightly, and on the hydrogen end is slightly positive because oxygen is polar. This is a polar covalent bond right here inside a water molecule. Anytime we have oxygen, it's going to make a polar covalent bond. Mostly. Let me say mostly on that. All right. And lastly, we got hydrogen bonds. So our hydrogen bonds are weak bonds. That's the first thing I want you to know about hydrogen bonds. These are weak bonds. Hydrogen bonds are what give water its shape. And so we want to associate hydrogen bonds with water. But they're weak bonds, so water makes them, and then it breaks them, and then it makes it and breaks it, and makes it and breaks it, and makes it, and as fast as it's making these hydrogen bonds, it's breaking these hydrogen bonds, but it's forming them and breaking them fast enough that there's always some hydrogen bonds formed to give water a shape. Like if you've ever filled up a cup of water and you see it dome up over the very top without running down the sides, those are the hydrogen bonds holding water on that surface. So hydrogen bonds we associate with water molecules. So I'm going to draw a couple of smaller water molecules up here. Yeah. Now let me get rid of that. So if I've got a water molecule, boom, here, and I'll have another water molecule here, and then we can have another water molecule here, and that's enough water molecules. Now we just said when we were forming our polar covalent bonds that the oxygen side of a water molecule is slightly negative. The hydrogen side of a water molecule is slightly positive. And that is where we form our polar, that is where we form our hydrogen bonds in between entire molecules of water. So there's a hydrogen bond there. There's a hydrogen bond there. Don't be fooled by the terminology here. This is not a hydrogen bond. Yes, it's bonded to a hydrogen, but this is the polar covalent bond. Hydrogen bonds we find between entire molecules of water. Oh. All right, so let's look real quick. At bonding strategies. And what I mean by this is how do we figure out what kind of bond it's forming or it's going to form? And I'll ask you, I'll show you an atom and be like, what kind of bond will this atom form? This is how we answer that. This is how we learn it. One, we look, is there a charge? Is there a charge associated with this atom or atoms that are about to bond together? If the answer is yes, if yes, then this is an ionic bond. Because if we have a charge, then we're talking about ions, and a bond between ions is an ionic bond. But if you answer no, you move down to question number 2. Are there multiple just meaning more than one, multiple molecules of water. Are there multiple molecules of water? Are there more than one molecule of water? Because if it's just one, then this doesn't apply. But if there are multiple molecules, emphasis on the plural there, multiple molecules of water, then we are looking at a hydrogen bond. Remember, hydrogen bonds, we find them in between the water molecules. So if there are multiple molecules of water, we're thinking hydrogen bond. But if we still said no, there's not a charge, there's not multiple molecules of water, then we look at number 3. Is oxygen present? Is there a molecule of oxygen? Like in a single molecule of water, there is one oxygen. So is oxygen present? If the answer is yes, then this is a polar covalent. A polar covalent bond if we see oxygen in there. Number 4. If you answered no to everything else, if no to above, I will say, if no to all these other questions, then we are dealing with a non-polar covalent bond. Now, this won't help you a ton in chemistry, maybe to get started, but this is going to help you a lot for chemistry for anatomy class, and that's why we're here. So these are my bonding strategies. We look, is there a charge? If so, it's an ionic bond. Are there multiple molecules of water? If so, it's a hydrogen bond. Is oxygen present? Is there an oxygen? Polar covalent? If no to all of these other questions, then we are looking at a non-polar covalent bond.